Okay, can you hear me? So, in the absence of Professor Mutlu, I'm going to continue today with a lecture about GPU programming. The first thing we are going to do, you see the title of the lecture is New Programming Features in Heterogeneous Systems. The first thing we are going to do is having a very quick review of what we were discussing in the previous lecture about GPU programming. And then we will finish that presentation with the two last points that are atomic operations and data transfers. We will see what are the implications of using atomic operations on GPU programs, and we will also see some possible way to optimize their use, and we will also see what to do with the data transfers, because remember, and we will review it right now, remember that every time you want to use a GPU, the first thing you have to do is moving the data to the GPU. So there's an inherent bottleneck there, and we have to deal with that. So it will be great that we can do something, maybe not always, maybe it's not always possible, but as long as possible, it will be nice to do something to optimize those memory accesses. Once we finish with these two topics, I will go through the rest of the presentation, new programming features. Probably today we will only have time to talk about collaborative computing, but if we have time, we can also introduce dynamic parallelism. Collaborative computing essentially means that it's going to be possible to have CPU and GPU collaborating, working on the same workload, using the same input data and generating the same output data or parts of this output data. So this is quite a new trend in GPU programming that is enabled thanks to new features that have very recently been released. Actually, these features started with the HSA architecture around 2014, and NVIDIA has incorporated them in their two latest generations in 2016. So let's start going through the slides. Very briefly review what we saw the other day about GPU computing. Remember that the traditional accelerator model requires the CPU to transfer data to the GPU. That's this number one. Oh, sorry. This number one. Once the data has arrived onto the GPU memory, then we have the GPU cores starting to work on that data and generating some output, some results. And when the kernel finishes, when the GPU finishes its computation, the results are moved back from the GPU memory to the CPU memory. That's what we call the traditional accelerator model. This slide, you're also familiar with this slide as well. Remember that we were saying that when we want to use GPUs in some program, what we will do is we are going to map serial or modestly parallel parts of the code onto the CPU cores, and those parts that are highly parallelizable, those parts that have essentially data parallelism, inherent data parallelism, can be offloaded onto the GPU. Remember also that here you can see the kernel syntax, not the kernel syntax, sorry, the kernel launch. And in this kernel launch, we can see the execution configuration, meaning the number of thread blocks that we are going to use and the number of threads within this thread block. Remember also that all the set of thread blocks that we launch onto the GPU is called the grid. So in this part of the slide, you see a grid of blocks of threads that executes some particular code called kernel onto the GPU. We were also taking a look at the memory hierarchy. Remember that there was global memory is like the main memory of the GPU. This global memory can be accessed from the host using these instructions, CUDA copy from the CPU to the GPU, or CUDA copy from the GPU to the CPU. So it was host to device or device to host. Each of the thread blocks can access some special fast on-chip memory that is called shared memory. The name of this, many people complain about this name. This is pure NVIDIA terminology. In OpenCL, for example, it is called local memory. Probably it's a better name for that. Essentially, it's a scratchpad. It's a software-managed cache. So as I was saying, all the threads in one thread block access this shared memory, this fast shared memory, and also each of the threads have their own, or can make use of their own registers. So also remember, we were talking the other day that these thread blocks are mapped onto the GPU cores, also called streaming multiprocessors or compute units, GPU compute units. So within each of these streaming multiprocessors, we have a shared memory, we have registers, and the register file is partitioned among the running threads. This is the traditional program structure. Just quickly review it. Remember that we, besides allocating memory on the main memory of the CPU, we also have to allocate memory onto the GPU memory. That's why we need to use this CUDA malloc. And then, as I said before, we have to move the data from the CPU memory to the GPU memory. So that's why we're going to use the CUDA main copy. Afterwards, we will launch the kernel. And when the kernel finishes, we will probably have to move data from the GPU memory to the CPU using, there you see point number 5, again, the CUDA main copy. In this slide, you have the complete syntax for each of these operations or instructions, CUDA malloc, CUDA main copy, the syntax of the kernel launch, and also the memory deallocation and the explicit synchronization. Remember that I mentioned the other day that this explicit synchronization is going to be used whenever we want to make sure that the kernel has finished. Just for one reason, because the kernel launch is asynchronous. Luckily, the kernel launch is asynchronous. This means that the CPU launches one kernel, and right after that, once the kernel is offloaded and the CPU is free, the CPU thread can start doing other stuff. And this is actually one of the features that we are going to use, or we are going to take into account in the second part of this lecture when we talk about collaborative computing. We also took a look the other day of how data is accessed by threads belonging to one thread block. Remember that, for example, in this particular example, we have an image, and this image is divided into different chunks or tiles. Each of them is assigned to one thread block, and each of the pixels is assigned to one thread. In this particular example, we are matching one GPU thread with one pixel. This is not the only way to do that. It's also possible to assign more computation to each thread. That is usually called thread coarsening, and it's one possible way of optimizing our code, essentially because we can obtain more instruction-level parallelism from doing that. It's something that can also be achieved using loop unrolling. You are also familiar with loop unrolling. These are like general optimization techniques. So the other day we saw how to access each of these pixels by one particular thread with an index, thread index.x, in a particular thread block with an index, block index.x, and a dimension that is block dim.x. The dimension is the size of the thread block. Remember also that we said the other day it's not always one-dimensional, as in this example, thread blocks and grids can also be two-dimensional or up to three-dimensional indeed. So, okay, and then afterwards we started talking about performance considerations. Remember that we talked about the latency hiding because GPUs are fine-grained, multi-threaded architectures. It is possible for them to hide the latency of long latency operations, for example, memory accesses to global memory, doing some computation, overlapping these memory accesses with computation on the cores. We also talk about how to optimize the memory access, the memory coalescing. We will review it right now, and also what to do when we have a lot of data reuse. Caches in GPUs are not so powerful as in CPUs, so it is good for the programmer to be able to manage, to handle this shared memory for data reuse. And the last thing we talked about was the SIMD utilization, what we call the intra-warp divergence, meaning that it might be possible, it might happen that not always all the threads belonging to one warp go through the same path, so this will obviously underutilize the GPU resources. So we'll very quickly review these things, and afterwards we will start talking about atomic operations and the data transfers. So remember, the latency hiding mechanism allows us to hide some long latency instructions. For example, in this case, instruction 4, the execution of instruction 4 by warp 0 is hidden by some other instructions, in this case from different warps, 2, 3, 1, etc. We should try to have the value of the occupancy, which is the ratio of active warps that we have in each GPU core. We should try to have it high enough to have enough thread level parallelism or warp level parallelism. Essentially, this means that it is good to have enough number of threads running on each SM so that long latency operations can be hidden by the execution of arithmetic, logical instructions on the cores by other warps. We also saw this slide about the occupancy. It might be necessary when we optimize code for the GPU, it might be necessary to calculate the occupancy, the number of warps that we have in each SM. And it is important to keep in mind what are the resources available in each of the GPU cores or in each of the streaming multiprocessors. For example, you see in the slide that the shared memory size is 64 kilobytes. So this means that if we have one program, one GPU program where each thread block needs to use 16 kilobytes, we can allocate up to 4 thread blocks in each SM. So, well, we will have some, maybe 100% occupancy in that case. But at some point, you might be optimizing your code, and for some reason, you might need to use a little bit more shared memory, and instead of using 16 kilobytes per thread block, you might need to use 17 kilobytes per thread block. In that case, you have to keep in mind that your occupancy will be reduced. Instead of having 4 thread blocks in each of the SMs, you're only going to be able to have 3 thread blocks in each of the SMs. This doesn't really mean that the performance is going to be worse, because we might have done some modification in the program that could be beneficial for the program. So there is no direct relation between the occupancy and the performance, okay? But usually it's good to have that in mind and try to increase the available TLP because of the latency hiding possibilities that I mentioned before. We also talked the other day about memory coalescing. Memory coalescing essentially means that we are going to have adjacent threads accessing adjacent memory addresses. Typically, the ideal memory access, we will have all the threads in one warp accessing all the bytes in one cache line. So that would be the most efficient access to memory. So that's why usually strided accesses are bad for GPU performance, because if the stride, depending on the stride that we have, we might need to access more cache lines. For example, a stride equal to means that each warp will access 2 cache lines. So essentially, this means 2 memory transactions, right? We were also discussing briefly the other day about what are the possible data layouts, and we mentioned that there are like 2 main layouts, structure of arrays or the array of structures, and we also saw some results that prove that structure of arrays is typically good for GPUs, while array of structures is typically good or better for CPUs. And after discussing about the memory, global memory access, we started talking about what to do when we have data reuse in one kernel, because we have many threads running at the same time. Many of these threads, some of these threads belong to the same thread block, and it might happen that at the same time or in different points in time, threads belonging to the same thread block need to access the same data or the same data elements. The example we saw the other day is this Gaussian filtering on an image. Remember that in this Gaussian filtering, what we do is a convolution for each particular pixel. We do the convolution of the pixels in the surrounding window with some particular Gaussian, it's called Gaussian kernel, is that like this green square that you see in the image. And recall that 2 threads belonging to the same thread block, for example, these 2 that are neighbors, they are going to access, or they're going to share some of the input pixels that they have to read, in particular these 6 pixels that you see in the image. So the best thing we could do in this case is not just doing coalesce memory accesses, or it's not just using the global memory efficiently. We can do it better, even better, if we divide the image into tiles and we first load each of these tiles into the shared memory, because afterwards the GPU threads are going to find the pixels in the shared memory, and the access is going to be much faster. Much faster means more than 1 order of magnitude faster. Just to give you some raw numbers, for example, typical shared memory access takes around 32 cycles, while typical global memory accesses take between 600 to 800 cycles. So that's a very important difference. But remember that even though the shared memory is very nice, because we can accelerate our computation a lot, we still have to take care of the fact that it's an interleaved memory. So it's a banked memory. We have to keep in mind how we access the memory, because if we have 2 threads belonging to the same warp which access the same bank, even though, especially if they access different elements, different locations in the same bank, we will have a bank conflict, and this will serialize the access, okay? We were also talking about the possibility of using hash functions or using padding to avoid these bank conflicts in some particular codes. And the last thing we discussed the other day was the SIMD utilization. Here in this slide and the next slide, you have like very toy example, some code that show how the threads execute this code. For example, in this case, we have that even threads go through the if, odd threads go through the else. So within each warp we are going to have divergence because some part of the threads, half of the threads go through the if, half of the threads go through the else. In some cases, we discussed briefly the other day the vector reduction example. In some cases, it might be able to put all the threads that are going to execute some particular part of the kernel together and group them in a more efficient way, as you see in the slide. So in this case, if the left half of the threads belong to the same warp, they will be running together, so we are using all the cores within the compute unit, within the SM at the same time. So we won't have divergence, so we are using the resources more efficiently. Okay, so this is the review until now. If you have any questions, let me know. And and then we are going to start with the atomic operations. So you all are familiar with the concept, with why atomic operations are needed. So I'm not going to talk about that. I'm just going to talk about how they are implemented in NVIDIA GPUs and what can we do to optimize their usage in one use case that I'm going to explain. So atomic operations, and in particular, we are going to focus on atomic operations on the shared memory, because also atomic operations on the global memory are possible. But for now, we are only going to talk about the shared memory. Atomic operations appeared in, they didn't appear from the very beginning of this GPU computing era. They started a little bit later with CUDA 2.0 and the compute capability 1.2. NVIDIA Compute Capability 1.2. And essentially, as you can see, we have the high-level instruction in CUDA. This is an example, atomic add. This means that we are going to add atomically some value that we have in this argument to the address that is pointed out by this pointer here. This atomic add has an intermediate representation that is called PTX. PTX is like an intermediate language that NVIDIA has and is independent of the architecture. In this case, you see that this is an atomic operation on shared memory. In particular, this atomic operation is an addition on unsigned 32 bits. So that's the meaning of this PTX syntax. As you see, these three registers indicate the output register, this R25. This RD14 contains the address that we are going to modify atomically, and R24 is the value that we are adding, contains the value that we are adding. So what the compiler does when we compile CUDA code, the first step is converting this high-level language, this high-level CUDA onto PTX, and afterwards, depending on the architecture, it is converted to different assembly that is called SAS in the NVIDIA stack. So you can observe, because here what we have is the name of 4 different generations of NVIDIA GPUs. You can observe that there is a difference between the code that was generated for Tesla, Fermi, or Kepler GPUs, and the code that is generated for Maxwell GPUs, at least for some of the atomic operations on Maxwell GPU, in particular this 32-bit integer, and 32-bit and 64-bit for atomic CAS. But what I want you to look at is how different these two codes are. In Maxwell, since 2014, we have native atomic operations. This means that the PTX instruction is translated into one single instruction, this atoms.add that you see in the slide. But previously, it was translated into 4 instructions or more. And these instructions, we can talk a little bit about them. These instructions essentially implement the atomic operation in a log update and log pattern. The first of the instructions is load from shared memory. So the LD means load, S means shared memory, and LK means log. So it's a load and log instruction. The second instruction, in this case, is an addition. The third instruction is store and unlock. And the last instruction is a branch. So as you can see, the first instruction contains one register, or has one register that contains the address that we want to modify. This R9 is the output register where we are going to store the value that we read from memory. And then we also have this P0. This is a predication register because this log update and log pattern is based on predication. You're already familiar with predication because Professor Mutlu explained it very recently. So how is this essentially working? Because actually you see that the P0 that is generated in the load and log instruction is afterward used by the addition and the store and the branch. Or actually, in this particular case, the store generates a new predication register that is later used by the branch, but it's essentially the same. Actually, it would be possible to do it with one single predication register. But how are these 4 instructions executed? Well, let's go to the most simple example. Let's assume that we have 2 threads. These 2 threads belong to the same warp, so they execute the instructions in lockstep. So they both are going to execute the first instruction together at the same time. So they both try to go to the shared memory, in this case, and read some value from shared memory. Observe that this is not a simple load instruction. It's a load and log. So at the same time, while the 2 threads are going to read one value from the shared memory, they also try to get a log. The log is associated to the particular shared memory address. So they both, the 2 threads, contend to get the log. And there is only one winner. The winner gets the log, so it will have 1 in its predicate register, while the other one will have 0. What does it mean? This means that the next instruction is only going to be executed by those threads that have the predication register equal to 1. So instruction add and instruction store are only going to be executed by that thread that won the match, okay, that got the log. And after storing, this thread unlocks the corresponding memory position. You can assume that this P1 contains the same value as P0. So this means that the threads that didn't execute the addition and the store operation will take the branch. So you see here, it is really clear that there is a serialization every time we have conflicts, every time we have different threads trying to update the same memory locations. Something similar also happens in the Maxwell architecture as well. But the good thing in the Maxwell architecture is that the atomic operations are native, so it is very likely that some arithmetic units were attached to the shared memory banks in order to have a more efficient computation. This is somehow something similar to what we call near data processing, right? Because we are putting some functional units next to the place where the data is stored, in this case, the shared memory of the GPU. So this is just in this slide, what we have is a very brief example of what I explained before. So if we have two threads, in this case, thread 0 and thread 1, that want to update atomically two different addresses in the shared memory, if these two addresses are in different banks and are different values, they are different addresses and are also in different banks, we can have concurrent access, meaning that both can read at the same time, modify at the same time, and store the result, the updated value at the same time. This takes some latency, let's call it T-base. But in case we have two threads accessing at the same time, or want to update at the same time the same memory address, we will have a conflict, and we will have some extra latency because of the serialization. One thing I also want you to keep in mind, this is shared memory, it's a banked memory, so even though two threads want to update different memory addresses, we might also have a problem if these two memory addresses are in the same bank. So we might have bank conflicts when we read in the load instruction and when we write in the store instruction. So keep that in mind, because this might be useful for your next homework that will be released tomorrow. Okay, so yeah, you see the difference between non-atomic conflict, concurrent updates, atomic conflict, serialized updates. So let's see an example of how to use these atomic operations. And the best example, the most representative example of the use of atomic operations on the GPU is the histogram calculation. You all are familiar with histogram. You all know what a histogram is, right? So it's a very simple operation, but at some point it might be tricky, especially when we have many threads working at the same time on the same histogram. That's the reason why we need to use atomic operations. So we assume what is called a scatter approach. What is a scatter approach? It's something like this. We assign the input elements to different threads, and these threads scatter the output onto some output array. In this case, is the histogram. Observe that the problem of doing this is that we might have conflicts, especially in the case of the histogram, where we need to use atomic addition. So you see in this example, we have thread 0, we have thread 2. They both want to update at the same time this bin number 1, so they will have a conflict, and their access to bin 1 will be serialized. In theory, it would be possible to do a different mapping, what is called a gather approach. In the gather approach, we assign the output elements to the different threads. So the good thing in that case would be that we won't need to use atomic operations. Why? Because each of the bins is assigned to one thread, and the thread is going to read the entire input and update the corresponding bin if the value of the input element is related or is the same as the histogram bin. Why the gather approach, even though it avoids the use of atomic operations, is not a good idea in the particular case of the generation of a histogram? Why is that? It's because of the size of the histogram and the size of the input image. Usually the size of an image is going to be very large. It's going to have hundreds of thousands of pixels, while the output, the histogram in this case, it's going to be maybe 100 of beans. 256 beans is a typical number of beans, right? So it doesn't make much sense to use only 256 threads to generate a 256 bean histogram in the GPU, because we would be wasting most of the cores that we have in the GPU, right? So that's why it is better in this case to use the scatter approach and process the histogram using atomic additions. The problem is that atomic operations might entail conflicts, and these conflicts, unfortunately, are going to be very frequent, especially in some of the cases, or many of the cases, where we are going to use histograms. Image processing. Every time we want to process some natural image, it happens that natural images have a lot of spatial correlation. As you can see, in some particular region of the image, the color or the intensity is very similar. So we have this example, if the slide, the forehead of this woman is more or less, all the pixels in the forehead are the same color, so their values are very similar, and it's going to be very frequent that two or more pixels that are executed at the same time, they belong to the same work, probably have to read different pixels containing the same value. So when we generate the histogram, they will have to update the same bean. So atomic conflicts are going to be very frequent in this kind of computation. So one way, this can be such a big problem if we try to implement a very naive histogram calculation on GPUs, because in summary, if we have all the threads of one image processing the histogram of, all the threads of one kernel processing or calculating the histogram of one image, in the end, we have only one single histogram. And at the end of the execution, this histogram will be computed, and this histogram is going to be stored into the global memory. So we have one single histogram in global memory. Think about that. If we just want to use this single histogram in global memory, what are the problems that we are going to have every time we have a conflict? Two threads reading, as in the previous slide, reading these two elements, value 192, they both go to global memory and read the pixels with value 192, and then they find, these two threads find that they have to update the same histogram being number 192. So they need to use atomic operations. They go to the global memory to read the bean, both together, read the bean, whatever the value is, update the bean, and then store. But they both are doing at the same time, so only one of them can do it. They both are accessing at the same time, so only one of them can do it in each time. So we have a serialization. Now think about what the serialization entails. Reading 800 cycles, modifying, writing 800 cycles, reading again 800 cycles, and so on. So this can take a lot of time. What can we do? We can use an optimization technique called privatization. And privatization essentially means that each of the thread blocks in the kernel are going to have one subhistogram, so that they only have to care about updating the beans of this subhistogram. We can split the image, the input image, into different chunks or tiles, and each of them, or several of them, could be assigned to different thread blocks. So, for example, in this case, you see that this is assigned to thread block 0, this is to thread block 1, and again, this piece here is also assigned to thread block 0. So each of the thread blocks, in this case we have, this part also, thread block 0. So we have 4 thread blocks. Each of the 4 thread blocks have its own subhistogram. They read the pixels, they generate this subhistogram, and when they finish, we need to merge, we need to reduce these subhistograms into a final histogram in global memory. So the good thing here is that we are reducing the total number of conflicts because threads belonging to different thread blocks aren't going to contend. And also, when we have contention, everything will be faster because we are updating beans in shared memory, which is much faster than the global memory. So as you see, it's quite a simple but effective optimization technique. So that's all regarding atomic operations and histogram calculation. And now I'm going to talk about data transfers. Recall in the beginning of the lecture, we talked about the typical program structure. We need to move data from the CPU memory to the GPU memory. We operate on this on this data in GPU memory, and afterwards we have to move back, or we have to move the results from the GPU memory to the CPU memory, right? So what's the problem here? The problem is that even though our GPU might be very, very fast, the data transfers, the memory transfers take some time. And there are many cases, I don't know if you, all of you or some of you might have already some experience with GPU programming. You might have seen that actually the data transfers can kill the performance of your application, GPU application, because even though your GPU might be very fast, the data transfers are quite slow. So there is some way to optimize this. We are going to discuss that. But first of all, let's keep in mind that usually with these data transfers, and you might remember that we need to use CUDAM and copy from host to device or CUDAM and copy from device to host. These data transfers are usually synchronous. This means that the CPU thread is locked until the transfer has completed. So these CUDAM and copy are blocking operations. In the general case, we will be using this CUDAM and copy, a blocking operation. Afterwards, we launch the kernel, and when the kernel finishes, we perform another blocking operation that is the copy from the GPU memory to the CPU memory. So these 3 steps, CPU to GPU data transfer, why that happened? These 3 steps, CPU to GPU data transfer, kernel execution, and GPU to CPU data transfer are executed in order, because actually that's the way it should be, right? In order for them to be executed in order, they belong to the same, what is called a stream. This is CUDA terminology. In OpenCL, these are called command queues. A stream or a command queue is a sequence of operations that are performed in order. Usually, when we are very beginner programmers and we want to write our code, we don't have to care about the string. We will be using the default stream. But it is possible to have more than one stream or more than one command queue. And this allows us to overlap. This is going to allows us to overlap communication and computation on the GPU. To that goal, we need to use some data transfer operations that are slightly different. They are called CUDAM and copy async. They are asynchronous data transfers. This means that the CPU doesn't need to wait for the data transfer to finish. They are non-blocking. And using these asynchronous transfers, it is possible to execute a transfer, start the computation for the data that have been transferred, and at the same time start the second data transfer. So in case we operate on some input data and so that the operations that we need to perform on this input data are independent, in case of having some, let's say, input image, and we can divide the input image into different parts, and the operation on this different part is independent of the other parts, we can divide the computation into several streams, so that the data transfers for one stream can be overlapped with the computation for another stream. Here you have a very simple example Here you have a very simple example in the slide. We are only considering CPU to GPU data transfers. For now, we forget about GPU to CPU data transfers. But in the baseline, where we have where we are using the default stream, we need to transfer all the data from the CPU to the GPU, and this takes some time. After that, we launch the kernel, and this takes some time, E in this case. So if the operations that we are doing on the input data are independent on other parts of this input data, we can divide into several streams. In this case, we are dividing into 4 streams, so that, you see, we transfer the first chunk of the input data. We start executing on this input data, and at the same time, we can start the next data transfer. So this is the way to achieve some overlap. In theory, the overlap that we can achieve is quite good, and as you see, there are some very raw estimates in the slide. So for depending on which of the 2 parts takes longer, the data transfers or the kernel execution, it will be the data transfers that hide the kernel execution, or the other way around. So for example, in this expression here on the left, we assume that the execution time of the kernel is greater than the transfer time. So in that case, we will see the execution time plus the transfer time divided, the total transfer time divided by the number of streams that we are using. That's more or less what you see in this figure. Or it could be the other way around, in case we have dominant transfers, because the transfer time is longer than the execution time of the kernel. So this can be useful in some applications. For example, video processing applications are very, very good case studies for this. Usually because in many video processing applications, we just need to apply always the same computation on each of the frames belonging to the video. So because the frames are going to be independent, we can maybe divide the entire input stream into some chunks of streams and transfer these chunks of streams, start computing on these, chunks of frames, transfer these chunks of frames, and while we are computing on some frames, 2 in this example here, we are transferring the next 2 frames. So we can save quite a bit of time. So that's what we can do so far to optimize the communication between CPU and GPU. This has actually improved in the latest generations. We will talk about that next, because now in the most NVIDIA and also AMD GPU generations, it's going to be possible for the GPU to produce page faults. So the CPU driver is going to have a migration engine that can automatically transfer memory pages from the CPU to the GPU. This is good for the programmer, but can also be good for performance. Not always, but in some cases can be good for performance. We will see some examples later. So this is the summary of the first part of the presentation. This is what we call the traditional accelerator model. And we have seen how the GPU programs are structured. We have discussed some performance considerations. And in today's lecture, we have taken a closer look at atomic operations and also how to optimize data transfers. Let's start with the second part of the presentation that is devoted to collaborative computing with CPU and GPU working on the same application. Let's talk about 10 minutes, and then we can have a break, okay? So very quickly review what we just reviewed, the traditional accelerator model, where we need to allocate our input in CPU using malloc, and the GPU using CUDA-malloc. We transfer using CUDA-memcopy from the CPU to the GPU, and then we also have to allocate our output. It's a duplicated allocation because we have to do it on the CPU memory and also on the GPU memory, and then we launch our kernel, and at some point, if we want, you know that this kernel launch is asynchronous, so if we want to make sure that the kernel launch has finished, we use this CUDA device synchronize, and afterwards, we can transfer the results back from the GPU to the CPU. So this is the traditional model, and as you see, the traditional model is a burden for the programmer because the programmer has to take care of allocating memory on the CPU, allocating memory on the GPU, and performing the data transfer for the input and for the output. Well, NVIDIA guys knew that, also OpenCL or AMD guys knew that as well, and they decided to do something that could, do some modification in the CUDA stack, or some addition to the CUDA stack that allow the programmer or frees the programmer from this burden. Okay, so that is what is called the unified memory. The unified memory appeared in CUDA 6.0 with the Kepler architecture in 2000. I don't know exactly, probably 2012 or 2013. And essentially, the unified memory in the beginning was just an additional layer that freed the programmer from doing this double allocation and these transfers. This is just handled by software. But more recently, with the Pascal architecture, and since CUDA 8, right now the newest version of CUDA is CUDA 9, for your reference. So with the Pascal architecture and CUDA 8, the unified memory was really unified. This means that the GPU can produce page faults, it is possible to allocate as much memory as we need, and in case the GPU is trying to access something that is not actually stored on the GPU memory, a page fault is produced. This page fault is forwarded to the CPU, and the CPU will take care of going to probably the disk for this page, and then migrate this page from the CPU memory to the GPU memory. And this can be transparently done for the programmer. So instead of using the CUDA-malloc that we have discussed, or we have mentioned until now, we use something called CUDA-malloc manage. And as you see, if you compare this code with the code in the previous slide, this is much simpler because actually we don't even need to use this malloc that you see in the first line. We just simply need to use this CUDA-malloc manage, and this allocates some memory in unified memory with a single pointer, and this pointer can be used by the CPU threads and by the GPU threads at the same time. So the good thing is that we just need to allocate the input, we allocate the output, we pass these pointers to the GPU kernel, and we don't even need to take care of the explicit data transfers. So by using this new feature, this unified memory, it's going to be much easier to have tight collaboration with CPU threads and GPU threads working at the same time on the same application. Until now, or until this unified memory and the, yeah, question? That's a good question, actually. Yes. So keep in mind that we are right now talking about NVIDIA GPUs. NVIDIA GPUs are discrete. Usually you have the CPU, you have the PCI Express in the middle, and then you have your GPU. So in this case, the unified memory is virtual unified memory. So in case it is possible for you to allocate some memory using CUDA-malloc manage, and if at some point the GPU threads need to read or write some data in unified memory that is not actually allocated in the GPU memory, then you will have a GPU page fault. This page fault is sent to the CPU. The CPU will take care of getting this page and migrate it to the GPU memory. So this is virtually unified, but physically separated memories. The thing is that this can be actually unified, physically unified. That's what we have in integrated devices. That there are, for example, we will see later some results, for example, for the AMD Kaveri, and this is a system on chip containing CPU cores and GPU cores within the same chip, and they are accessing exactly the same memory. So in that case, we have one single memory, physical memory, that is handled also as one single memory space. So it's not only physically, but also virtually unified. But that's a good question. But keep in mind that I'm mostly explaining everything from the programming point of view. So that's why I don't explicitly say when we have a physical unified memory or virtual unified memory. But it's good that you have these questions. Okay. Okay, so I think that we are going to stop here for now. Let's take a break, 7 minutes, and we will continue. Okay, let's continue. So as I was saying, the main goal of this part of the presentation is talking about how CPU and GPU can collaborate on the same workload, on the same application. This, in the traditional accelerator model, this is possible, or this has been possible, but in a coarse-grained way. That's essentially what we saw in the beginning of the presentation. where we saw that some serial part that was executed by the CPU threads and the data parallel parts that were executed by the GPU threads. Usually, we don't even have concurrent execution of CPU and GPU. Even though the kernel launch is asynchronous, typical traditional GPU applications, just the CPU just offload the execution to the kernel, the computation to the kernel, and just waits for the GPU to finish and maybe then do some very fast serial computation and again launch a new kernel. So that's usually the traditional approach. If we actually want to have CPU threads and GPU threads working at the same time because somehow we want to have more performance, we want to have improved performance, the only way we could do that in the traditional model was taking advantage of the asynchronous, of the asynchronous kernel launch. Remember that this means that the CPU thread that is executing these instructions reaches the GPU kernel launches the kernel, and after that it is free to continue the execution. So maybe it could be possible to do some, for the CPU thread, to do some computation here before the GPU kernel finished. But still, this is not very convenient, so actually not many programmers use something like that. Also because, as you can imagine, the CPU needs to operate on the CPU array, the GPU needs to operate on the GPU array that has been allocated on the GPU memory, so they both are working on different arrays, even though in the end they will be somehow merged. But actually, if they are merged, the programmer has to make sure that they both are working on different parts. So, for example, let's go back to the example of the histogram, and we could have, for instance, CPU thread computing some bins and GPU threads computing the other part of the histogram, different bins. We have to make sure that if we want to afterward merge these two parts of the histogram, they have operated on different parts of the histogram, right? Actually, it's not very convenient to use this approach, so that's why most of the people didn't use it. But with the new heterogeneous features that recently appeared, it's going to be possible to do that. Recall that using unified memory, we can have one single memory allocation, and we are going to be able to have the CPU threads and the GPU threads working at the same time with some input data and some output data. And actually, it's going to be possible even to have CPU threads and GPU threads updating actually the same output locations, the same output elements. So in the code in the slide, you see how the input is allocated, the output is allocated, and right after that, the GPU kernel is launched. The CPU passes to the GPU this output and these input pointers. And right after that, the CPU can start using also this input and output. So while the CPU is executing these instructions here, the GPU is also executing some other instructions. You don't see them in the slide because they are obviously in a different function, in the kernel. But they both are using input and output at the same time. So it is even possible for them to access the same memory addresses at the same time. And this is thanks to the fact that The latest GPU architectures have enabled this CPU and GPU memory coherence, and also the possibility of having system-wide atomic operations. I'm not going to talk about memory coherence because this is a topic that will be later covered in the course. But essentially, what you have to keep in mind is that some data can be read by the CPU, can be read by the GPU. It can be in both GPU caches and CPU caches, and it's at some point this data is modified by one of the sites. It will be automatically invalidated on the other side, so that the corresponding site always reads updated data. So this memory coherence is not only available on the two most recent NVIDIA generations, Pascal and Volta, but it's also available on some AMD devices since the appearance of the HSA architecture. And that's why these features are incorporated into CUDA. You're already familiar with CUDA malloc manage. Also, the system-wide atomics have a similar syntax to the atomic operations that we saw in the beginning of the lecture, but with this suffix, atomic at system, to indicate that they are system-wide atomic operations. And similar features are also available in other programming languages, such as OpenCL 2.0. Where we have usually the syntax in OpenCL is usually more complex than in CUDA, but as you can see, it is also possible to allocate some shared virtual memory, which is the same concept as the unified memory in CUDA. And it's also possible to have these system-wide atomic operations. This syntax, as you see here, is C++11 syntax. I don't know if you are familiar with C++11 atomics. It is possible in C++11 to indicate the memory scope, and in particular, when we want to use system-wide atomics, we need to use this all SVM devices memory scope, just to indicate that this, in this case, this each H out can be modified from any of the available devices in the system. In the particular case we are discussing, these devices are CPU cores or CPU or GPU, okay? And this is one more example, is C++ AMP. I don't know if you are familiar with C++ AMP. It's a higher level programming language. It also has a similar concept, in this case, in the HSA architecture, actually, that uses this C++ AMP, or can be programmed with this C++ AMP. The similar concept is the unified memory space. It is even simpler in C++ AMP because we just need to use malloc, but afterwards this H-in can be accessed from CPU, from GPU, or from any other device that could potentially deploy also these heterogeneous features. In HSA, instead of talking about system-wide atomics, we talk about platform atomics, but they are essentially the same. And as you see, the syntax is also C++11, so it's equivalent. So now we are going to start, even though we are not going to have the chance, at least today, to take a look at the any code in detail and see how to do that. But we are going to start discussing about the possibilities, how these features can be used to have a tight collaboration between CPU threads and GPU threads. So that's what we call the collaborative patterns. Before starting with the collaborative patterns themselves, let's take a look at the program structure. We are going to consider that we need to execute some tasks. Each of these tasks can be decomposed into several, in this case 2, sequential subtasks. And usually we are going to have many of these tasks. That's why we want to have many threads working on these tasks at the same time. So these are data parallel tasks. Usually these data parallel tasks compose what we call a kernel, a GPU kernel. And you know that every time we finish or we terminate a GPU kernel, we have some kind of coarse-grained synchronization. In the traditional GPU programming model, each of these data parallel tasks can be assigned to one GPU thread. Remember that these GPU threads are organized into thread blocks, and when all the thread blocks in one kernel finish, the kernel finishes, and at that point we have a coarse-grained synchronization point. And right after that, we can launch a new kernel, right? And this new kernel will also have some data parallel tasks, different or the same parallel tasks that are going to be assigned to the different threads that are going to execute them. So the very first thing that we could do to have a collaborative pattern is what we call the data partitioning. Keep in mind, and actually that's conceptually the simplest thing, keep in mind that we have data parallel tasks, we have data parallelism, so what if we have 2 or more devices in our system, what we are going to do is that we are going to assign some of the data parallel tasks to one of the devices and the other part to the other device. In case these 2 devices are different, so same as CPUs and GPUs are different, they might be faster or slower executing this data parallel task or executing these subtasks. So that's why you see in the slide that this particular yellow subtask is shorter in device 1 than in device 2. When the yellow subtask is completed, then the threads, CPU threads or GPU threads, execute the green one. And they continue executing them until all the data parallel tasks have finished. What it was previously executed by one single GPU kernel, now the computation is distributed among CPU threads and GPU threads, or device 1 threads and device 2 threads. So then we have the coarse-grained synchronization, and afterwards we have the data partitioning of the tasks of the second kernel. So that's what we call the data partitioning. Usually one thing we are going to do here is that depending on how powerful each of the devices is, we will assign more tasks to one device or to the other device. Okay? Is this possible in previous generations, or this is only possible in current architectures with these new features that I previously introduced? This is something that can be done in previous architectures as well. But if you don't have the new heterogeneous features, it's going to be a little bit more complicated. And essentially, you might need to profile your application before finding the sweet spot, before finding the most optimal distribution of the data parallel tasks among the different devices. We will see some examples next. Another way of doing this is, actually, let's go back. If you look at this part of the slide, on the right part of the slide, you see that the first task takes a little bit shorter in device 2 than in device 1. I mean the entire task, while the tasks in the second kernel take shorter in device 1 than in device 2. So one thing we could do is assigning those tasks to the device that executes them faster. So we could do something like that. That's why we call it coarse-grained task partitioning. We assign the entire tasks to the device that is faster for these tasks. Observe that it is still possible to have some concurrent execution with this coarse-grained task partitioning approach, even though you don't see that in the slide. How is it possible? For example, let's assume that we are processing a video stream that is composed by many frames, and for each of the frames, we execute some computation on the GPU, and afterwards, some computation on the CPU, or the other way around. Because they are working with different frames, and different frames are independent, we can have some kind of pipeline, right? So we could have, on the left side, on device 1, we could be working on one frame, while device 2 is working with the next frame. So it's, this approach is more or less similar to pipeline execution. And the third possibility is what we call the fine-grained task partitioning. And actually, this is something that it's only enabled by these new heterogeneous features that we are presenting in this lecture. So the idea is that we will assign these subtasks to the threads that execute them faster. So, for example, the yellow subtask is faster on device 1, so we're going to execute it on device 1. The green subtask is faster on device 2. We are going to execute them all on device 2. In this case, it's going to be needed to have some kind of fine-grained synchronization between the devices. And this fine-grained synchronization, there might be different ways to implement it, but it's only enabled, I mean, one of the possibilities is using system-wide atomic operations. For example, we could have an array of flags, and when the CPU finishes with the yellow subtask, the CPU thread updates one flag, and when this flag is set, the GPU threads know that the corresponding yellow subtask have finished, so some, maybe one or several GPU threads can start working on that data instance that was previously computed by device 1. So this is what we could have. Some part of the computation on the CPU, part on the computation on the GPU. You see that it's possible, and you see in the slide that it's possible to have concurrent execution of CPU and GPU, and in the middle we will need to use some fine-grained synchronization between CPU threads and GPU threads. At some point we will have the coarse-grained synchronization, and then again, fine-grained data partitioning on the second kernel. Obviously, it is possible to, in one particular application, it is possible to combine these different approaches. So maybe for one particular kernel, we have the fine-grained task partitioning, but then for the next kernel, we have the data partitioning. So it's something that is going to be possible in real applications. So let's start taking a look at some use cases that can take advantage of these features and can implement these approaches. For example, the very first one is histogram. We already talked about histogram in the beginning of the lecture. Now let's talk about histogram again. Actually, this is a very naive example, but still we can get some performance improvement from doing some or implementing some data partitioning. In this case, what you see in this slide is the traditional, so it's a collaborative pattern, but from the point of view of the traditional accelerator model. Observe on the right part of the slide where you see the code, we need to allocate the image on the CPU, we allocate the image on the GPU, we need to transfer the image from the CPU memory to the GPU memory, so from host to device, and then we also need to double allocate the output histogram in CPU memory and in GPU memory. After that, even though it's not explicitly presented in this code, we launch CPU threads and we launch GPU kernel. And they are going to operate, in this case, we are doing some input partitioning because we are dividing the image into two parts, and one part is assigned to the CPU threads, and the other part is assigned to the GPU threads. So probably, because this is a data parallel computation or data parallel operation, we are going to assign more pixels to the GPU that probably will be more powerful for this operation than to the CPU. But CPU cores and GPU cores, or SMs, are reading pixels, input pixels from the CPU memory or from the GPU memory and generating their own partial histogram. So at the end of the computation of the CPU threads or at the end of the GPU kernel, we have two subhistograms, one of them in CPU memory, the other one in GPU memory, and in the end we will have to merge them, maybe because the histogram probably won't be too large. We just need to use one CPU thread or several CPU threads to do this merging. This is this is simple. This is actually quite easy to write, but it can be even easier if we use a unified memory. Because you know that in unified memory, we just need to allocate the histogram, the image once, and the histogram once. We launch the CPU threads, we launch the GPU threads, they start reading input pixels. Still, we can have some input partitioning, and in this case, you see this is kind of a static partitioning because we are dividing the image in the beginning in two separate parts, and CPU and GPU take care of the corresponding part only, but they are only using one single histogram that is allocated in unified memory, and by using the system-wide atomic operations, you see here this atomic add system, they are directly updating the output histogram. So no need to have this double allocation of the histogram and later merging. So this is the most simple case study, and as you see, a first example of what we can do with these new heterogeneous features. Okay, any questions so far? Yeah, I'm not going to show you results for histogram. But let me, that's a very good point. But let me explain you. So again, I'm just focusing on the possibilities of, from the programming point of view, okay? That's the main goal here. Also, if you consider, if the system that you have in mind is NVIDIA system or AMD, but with a discrete AMD GPU, you have two different devices with two different memories. Even though we have the unified memory or the shared virtual memory, and it's possible for the GPU threads to access something that has been allocated on the CPU side, it will take quite a bit of time, because every time we want these threads here access data that, in this case, output bins that are on the other side, we need a page fault. We need to bring the page to the GPU memory in this case, and we update the corresponding bin in the GPU memory. If just milliseconds later, one CPU thread wants to update the same bin, we will have to migrate this page back from the GPU memory to the CPU. So that's why this is not very efficient from the performance point of view. It is different if we have an integrated architecture, where CPU and GPU are in the same chip and they use the same memory. In that case, it might be worth doing this approach, because we are accessing the same memory space. Okay? Okay. The next case study is called Bezier surfaces. I don't know if you're familiar with Bezier surfaces. These are some kind of geometric structures that are using graphics. And essentially what we do is generating a surface using a set of control points. In the image, what you see is what is called a B-cubic Bezier surface that is generated from a net of 4 times 4 control points. And depending on the position of the relative position of the control points, we have a different shape of the surface. This surface, or the surface points, are generated using these two expressions, what are called the Bernstein polynomials. And as you see, each of the points of the surface, S, U, V, is obtained using the control points P, I, J, and the Bernstein polynomials that are in equation 2. In this case, this is a very regular computation. The amount of computation that we need to do to calculate each of the output points, each of the points in the output surface, is the same. So it's very regular. And in this case, using a static distribution in a collaborative approach can be good enough for having good performance. What is a static distribution? Well, essentially means that we have our surface. We need to calculate all the points in the surface, and we are going to assign part of these points to one device and the other part to another device. Again, same as I said for the histogram, because this is there is a lot of data parallelism here. We can do some data partitioning approach here, and most of the points will probably be assigned to the GPU side, while a smaller part of the points are assigned to the CPU side. For each of the points, as you can see, we have to calculate the 3 dimensions, X, Y, and Z. So is it possible to implement this with the traditional model? Yes, it's possible to do this without unified memory, because we could allocate the control points on the CPU, control points on the CPU in the GPU. We can transfer the control points from the CPU to the GPU. We also allocate 2 surfaces, or part of the surface in each of the devices, and we can launch CPU threads and a GPU kernel to compute the corresponding part. And in the end, we synchronize. We synchronize, and after the synchronization, we are sure that both CPU and GPU have finished with the corresponding part of the surface, and then we somehow need to copy the part of the surface that has been generated on the GPU and is on GPU memory, copy it back to CPU memory. So that is the way we should write the code if we want to have this data partitioning approach in the traditional model. Let's take a look at some results. Actually, these results are on an NVIDIA Jetson TX1. Don't know if you are familiar with NVIDIA Jetson TX1. It's a mobile platform containing 4 ARM processor and 1 GPU with 2 cores, with 2 GPU cores. And in this case, the results that you see in the slide are the execution time for calculating a Bezier surface with a square Bezier surface, B-cubic surface, 300 times 300 points. And if we want to implement a static partitioning, as we saw in the 2 previous slides, we will have to profile the application in advance, or the algorithm in advance, to find the sweet spot. In this particular case, for this particular platform, the sweet spot is 20% of the tiles, or 20% of the surface assigned to the CPU threads, and the remaining 80% of the surface assigned to the GPU threads. So the speed up that we can obtain with respect to GPU-only implementation is 17%. As I said, this Bezier surface computation is very regular. So probably even though we might need to generate many more Bezier surfaces on this system, we might not need to profile this again and again, because the computation is very regular, and afterwards we need to compute a new surface. So probably the 20% distribution is going to be still the sweet spot, no matter what surface are we calculating. But consider that we could be doing some more complex computation, or maybe more input-dependent computation, where the amount of computation on each of the points might not be exactly the same. So in that case, this static approach is not so nice, because we might need to profile in advance or have some kind of online profiling in order to find the sweet spot. So even though this is a good case for static partitioning, not always we are going to have such a favorable situation. If we want to use unified memory, these new heterogeneous features, we can do it. And actually, programming is much more simple. We don't have to double allocate. We don't have to care about data transfers. And in the end, we will have actually CPU and GPU working exactly on the same surface that has been allocated only once. It's this surface that you see in this code. And also, with the new features, it is possible to have some kind of dynamic distribution. And this is going to be especially useful in cases where the computation is not so regular, where the amount of computation needed for each of the output values might be different. So in those cases, we could have some dynamic distribution. For example, one simple way to implement this dynamic distribution is having some kind of queue, in this case a queue of tiles, and every time the CPU threads or the GPU thread blocks or the GPU threads finish with the computation of one tile, they just need to go to this queue and fetch a new tile and start operating on this tile. This can be very simple. I mean, there might be other ways of implementing this, but the most simple way of implementing this is having like a global counter, in this case, this tile num, and add 1 to this tile number, and with this atomic add system, and get a tile number, and start operating with this tile number. So something like this can be done. This is GPU code, what you see in the slide, but a similar thing can be done on the CPU. GPU threads are working on some tiles. CPU threads are working on some tiles, GPU threads working on other tiles. Every time they finish with one tile, go to the queue, fetch a new tile, and start computing. And we can have load balancing among both sides in a, let's say, automatic way. We don't need to care about static profiling as we did before. The results that you see in the screen are actually for such an implementation with a dynamic distribution. These results have been obtained on an AMD Kaveri. It's an integrated CPU plus GPU system with 4 AMD Steamroller CPU cores and GPU with 8 compute units. And the results that you see in the graph are the execution time for one Bezier surface for 3 different cases with different number of control points, and the results are for 1 to 4 CPUs, CPU-only implementation, GPU-only implementation, and then on the right, the collaborative implementation that uses CPU and GPU at the same time. Because this kernel or this particular algorithm has a lot of parallelism, and the computation, it's quite a bit compute bound in this particular platform. It's not so limited by the memory access as other codes. Actually, the next example is like that. We see some improvement from using all the resources at the same time, up to 47% improvement over the GPU-only version. And this is possible on the AMD Kaveri, using very similar features as the ones we are explaining for NVIDIA systems. Any questions? Okay. Let's go ahead with the next case study. This is padding. We are also going to use data partitioning in this padding example. Not only in this one, but also in the next one, that is string compaction. I guess you all are familiar with padding. Padding essentially, or matrix padding essentially means adding some extra columns to a matrix, something like what you see in the slide. And this matrix padding is an operator that can be, or a primitive that can be useful in many applications. For example, for memory alignment, because we want to have better vector utilization afterwards, or better cache locality can also be obtained by using matrix padding. And also in some other primitives or algorithms, like the transposition, the in-place transposition of matrices can also be very helpful. You all know what's the transposition, and if you think about implementing transposition in place, in principle, you might think that this is not challenging at all, because, well, transposition just means swapping elements over the diagonal of the matrix, right? That's what we usually have in mind when we think about matrix transposition, and in particular, if we think about in-place matrix transposition. In place means that the output matrix will be exactly in the same place as input matrix. So, but actually, this is as simple only in square matrices, where we just need to swap elements that are at the same distance of the diagonal. If we want to implement the in-place transposition of rectangular matrices, in general, the algorithm that we need to use is much more complex. But if this rectangular matrix is near square, or even though it's not near square, but in case it's near square, we can simply padding maybe a few columns, and afterwards we can implement this transposition using the simple approach that is possible for square matrices. I mean, this is just one example of possible use of matrix padding. So again, in principle, let's forget the in-place transposition. Let's only talk about out-of-place, sorry, not transposition. Forget about in-place operation. Let's talk about out-of-place, in this case, out-of-place padding. And what we could do here, because we want to insert some additional column or columns in this matrix, what we could do is dividing because the matrix is divided into different rows. So maybe what we could do is assigning these rows to different CPU threads or to different GPU blocks, GPU thread blocks, so that each of the CPU threads or each of the GPU blocks is in charge of moving each of the matrix rows to the corresponding place. Well, we can do that, again, on our NVIDIA Jetson TX1, and we see some improvement from doing that. We are assigning, if we assign, for example, how much is this? Is 30% of the matrix is assigned to the CPU threads, the rest is assigned to the GPU threads, and we can obtain up to 29% of the 29% speed up with respect to the GPU-only version, because the CPU threads are also collaborating. This is fine, but it could be even better if we can have they both working. If we don't need to do this kind of static distribution, it could be even better if we can do this in a dynamic way, and this is possible with the new heterogeneous features. In the example, in the slide, what you are going to see is some way to do exactly the same, but operating in place. And this is only possible with the new features like the unified memory, memory coherence, and the system-wide atomics. Let's say that we have some GPU thread blocks and we have some CPU threads that are going to include one extra column in this matrix that you see here. The result will be what you see here, but in the end is the same with a different representation, is the same as what you have on the left. So let's generate the matrix on the left with GPU and CPU working at the same time, and also let's do it in place, which is the challenging part. So we can have CPU threads reading one particular row, in this case, this blue or purple row that you see here. We start reading this row, and we store it in some temporary location, for example, in some registers. At the same time, we can have the GPU thread blocks reading different rows. So each of these rows can be assigned to a different GPU thread block. Observe that the problem here, because we want to pad one column, and padding essentially means that the rows need to be moved from lower address to higher address memory locations. So this blue row, that is the last row of the matrix, will be moved to some memory locations that are at the bottom of the figure. So the problem here is that this orange row that you see here, when it is in the final destination, probably it will need to overwrite some of these blue or purple elements of this row. That's the problem, or that's the challenge of implementing the in-place matrix padding. So what we can do is using an array of flags, and every time each of these rows has been saved in the temporary location, the corresponding worker, the CPU thread or the GPU threads, will set the flag, indicating to the rest of workers that the corresponding row has already been saved, so these memory positions can already be overwritten when we shift the row to a higher address memory location. So as soon as in this case, the CPU has saved the row in the temporary location, we set the flag, and we can start writing to the final destination. So when this GPU thread block finishes loading the row, the corresponding orange row in the GPU temporary location, it sets the corresponding flag, and because this blue flag has been set before, the GPU thread block knows that it can start writing to the final destination. So that's the way all the thread blocks are going to operate, and in the end, we will reach our final matrix with the extra column. So this could potentially give us some benefit as well. Actually, you saw some benefit of doing this collaborative approach for the matrix padding on the NVIDIA Jetson. It maybe is not always the case on every system. For example, in the AMD Kaveri, because this is a very memory-bound operation, we are essentially reading from memory and writing to other memory locations. So there is not much computation in this algorithm. We actually, depending on the configuration, here you see workgroups and GPU workgroups, which is the equivalent concept in OpenCL for the NVIDIA CUDA thread blocks. So depending on the execution configuration that we choose, we might not obtain any improvement from using the collaborative approach. So you see, this is the throughput, the performance, so higher is better for the GPU-only version, and it's faster than doing that with GPU plus 1 CPU thread or 2 CPU threads or 4 CPU threads. But essentially, the reason why this happens is because, as I said, this is a very memory-bound kernel, so we don't obtain any benefit because by just using the GPU, we are already exploiting almost all the available bandwidth. Actually, you can compare the results for the padding, which are the blue bars on the left, with the GPU stream benchmark on the right, and you see that the obtained throughput is very similar. I don't know if you are familiar with the stream benchmark. Essentially, it's a micro benchmark to measure the maximum bandwidth that is available on a system. So in this case, is a GPU version of the stream benchmark. So because this is such a memory-bound operation, this matrix padding, we are not obtaining much improvement from doing this collaboration in this particular AMD Kaveri. I just want to show you results for string compaction, and we will have a break. String compaction is similar to matrix padding because we are also moving data, but instead of moving data from higher address to lower address memory locations, we are doing it the other way around, because in a string compaction, what we want to do is filtering. We want to remove some elements. For example, in the slide, what you see is that we are going to remove those elements that are equal to 0. So the computation is very similar to matrix padding, but there is actually a little bit more computation. It's more irregular in the sense that we can divide the input array into different chunks, and each of the chunks is going to be assigned to GPU thread blocks or to CPU threads, and each of these GPU thread blocks or CPU threads need to count how many elements should be moved and how many elements are going to be removed. And also, they will have to communicate to the other workers how many elements actually are going to be stored in the final array. So, for example, consider that that these first 4 elements are assigned to one GPU thread block, and these 4 elements assigned to the next GPU thread block. So this GPU thread block should know how many elements are actually going to be copied from the input to the output, so that these 3 elements that were assigned to the second thread block are stored in the corresponding destination. Okay? So we need some kind of communication across thread blocks. I'm not going to explain that. I just want to show you the results. This is also data partitioning, and what I just wanted to remark is that even though it is similar to matrix padding, there is more computation because we actually need to count how many elements are going actually to be moved to the output array. These are results for the NVIDIA Jetson TX1 up to 25 speed up with respect to the GPU only version, and these are results on the AMD Kaveri. You see up to 82% improvement with respect to the GPU-only version from using up to 4 CPU threads on the AMD Kaveri. So also in this case, we have some benefit from the collaboration. Okay, we already finished with the data partitioning case studies. Let's take, again, a 7-minute break, and we will continue with some examples of the task partitioning. Okay? Thank you. Okay, let's continue with our next case study. It's task partitioning. And we are going to apply this task partitioning. Actually, I would say that this is kind of coarse-grained task partitioning, as you will see. We are going to apply this to the breadth-first search algorithm. Before explaining the task partitioning strategy, what I'm going to do is explaining how we can, because before thinking about how to distribute the computation between CPU and GPU, it's good to know the algorithm and know how we can map this algorithm onto the GPU. So that's why I'm going to explain first one approach that is called the top-down approach, and two possible implementations, GPU implementations, two possible kernels for this top-down approach. It is called the top-down approach because we are going to start the computation from one particular node that is going to be the source of in our algorithm and in our graph, and we are going to visit all the nodes belonging, or all the vertices belonging to the graph in successive iterations. I assume that you are familiar with breadth-first search. Otherwise, I can briefly explain it. So let's draw a graph. Each of these is a different vertex node. This is 0, that actually is going to be your source. This is vertex 1, 2, 3, 4, and 5. And then we have some edges between these vertices. So for example, something like this. So we already have our graph. In breadth-first search, what we essentially do is starting from one vertex, we are going to calculate the distance from this vertex to any other vertex in the graph. So this is very simple, and as you see, this would be in level, well, this is level 0, these two are in level 1, this is level 2, this is also level 2, and this is level 3. So that's how we execute this breadth-first search. And in the top-down approach, what we have is we are going to process this iteratively, and we are going to, in each of the iterations, we are going to handle one frontier, and we are going to visit all the neighbors of each vertex in the frontier. So in the very first iteration, let's call it iteration 0, in our frontier, we only have one vertex, that is vertex 0. So as you see, this we will explore the neighbor. I mean, in this from this vertex 0, we can visit other vertices, which will be our output frontier and also the input frontier of the next iteration, iteration 1. So from this vertex 0, we visit the neighbors that in this case are vertex 1 and vertex 2. So the output of iteration 0 is a frontier containing vertex 1 and vertex 2. And this is the input for the next iteration. In iteration 1, we have input vertex 1 and input vertex 2, and our output frontier will have the neighbors of this vertex 1, which are 3 and 4, and the neighbors of this vertex 2 that are 1 and 4. In principle, we might also have them here, although probably we won't have them because they have already been visited. Okay, but anyway, let's assume that we have them there. So how can we parallelize this on the GPU? So consider that on the GPU we have many thread blocks and we have many threads in each thread block. So what we have to do is distribute the elements for this top-down approach, distribute the elements that are in the frontier, the vertices that are in the frontier, among the different threads that we are executing so that each of the vertices in the frontier is assigned to one thread, and this thread is in charge of visiting the neighbors of the vertex that has been assigned to it, and include these neighbors in the output frontier. So what we will have in iteration 0, we use one thread, thread 0, and this thread 0 visits the neighbors of vertex 0 and stores them in the output queue, in the output frontier. At the end, we need to finish the kernel. We will launch, we might not need to finish the kernel. Let's say that we finish the frontier, and then for the next frontier, we assign one thread here, and we assign one thread here. And for the next frontier, for iteration number 2, we have one thread here, here, and here. And they will populate the output queue with the corresponding neighbors. Okay? Now, think that the size of the frontier might change, right? Depending on the graph, but not only depending on the size of the graph, also depending on the particular iteration in the graph. So in the very beginning, observe that we are only using one thread, which is thread 0. So probably we are launching one kernel for one single thread. In the second iteration, or in iteration 1, we might need more threads, right? How many? That will depend on how many neighbors thread 0 have, vertex 0 has. In this simple example, it's only 2 neighbors, but in some graphs, might be hundreds or thousands. So for example, think about social networks. I guess you know that one way of representing the connections between social network users is using graphs. And each of us can be a vertex in one of these graphs, and depending on the number of friends that each of us have in Facebook or any other network, we will have so many neighbors, right? So maybe, I don't know, maybe some of us only have 2 or 3 friends, but there might be other people, famous people, for example, who have hundreds or millions of friends or followers, right? So this might be very dependent on the graph, but also very dependent on the iteration, very dependent on the way the graph is explored. If we assume that the graphs that we are using are small, or we assume that the frontiers for the BFS exploration of these graphs is small, it might be enough with just one single thread block. So for example, consider that this is our graph. You see that the graph is very small. And actually, the largest frontier that we have here in this example is 4. if we only have 4 vertices in the frontier, how many thread blocks are we going to use? It will be enough with 1 single thread block, right? Probably it will be enough with 4 threads in 1 thread block. So when I talk about kernel 1 in the slides, I mean a kernel with very small frontiers. The good thing of having very small frontiers is that we don't need to terminate the kernel because we are only going to use 1 thread block. And the good thing of using 1 single thread block is that we can synchronize the threads that belong to the same thread block with, you remember these sync threads that we presented in our previous lecture. So we don't need to terminate the kernel in this case. But what happens if all frontiers are very large? What happens if our frontiers have thousands of elements? Then we will need to use more than 1 thread block. And if we need to use more than 1 thread block, we will be dividing each frontier in different parts, different chunks that are assigned to different thread blocks, block 0, block 1, and so on. In the end, each of these thread blocks will generate the next frontier, the output queue, but before processing this output queue as the input frontier for the next iteration, we will have to terminate the kernel and launch 1 new kernel. That's what we call in the slides kernel 2. For very large frontiers, more than 1 thread block, and this requires kernel termination and relaunch. Okay? So these are the 2 approaches that we initially consider in this slide when we talk about the top-down approach. It's not the only way of implementing BFS on GPU. There's a different approach, for example, called bottom-up approach, where we assign threads to each of the vertices, and every thread checks if the vertex is being visited in each of the iterations or not. The problem with this vertex-based approach, with this bottom-up approach, is that we might have many idle threads. We might be launching many threads, but this thread might be idle. In the top-down approach, the good thing is that all the threads, or almost all the threads that are launched, are actually working, even though it might have some problems with irregular memory accesses, but we are not going to discuss that. So the first thing I want to explain is that it is possible to have an intermediate solution between kernel 1 and kernel 2. This, we could talk about we could call it kernel 3, right? And this is going to use some atomic-based block synchronization. There is some way of synchronizing thread blocks without terminating the kernel and relaunching a new kernel. And once we explain this atomic-based block synchronization, then we will be able to discuss the collaborative implementation. So what we do essentially in this kernel 3, this new implementation that avoids the kernel relaunch, is somehow combining kernel 1 and kernel 2. Instead of launching as many thread blocks as needed by the frontier size, what we are going to do is launching as many thread blocks as can fit on the GPU running at the same time. So in this picture, you see the example. Let's assume that we have a very wimpy GPU with just 2 cores, 2 SMs, SM0 and SM1. And depending on, you know already that depending on the occupancy, we might have more or less number of thread blocks in each of the SMs. So let's assume that in each of the SMs, we can have 2 thread blocks running. In this snapshot, what we have is thread block 0 and thread block 1 are running on SM0, 2 and 3, and running on SM1. Okay? But our frontier is much larger than what thread 0 to 3 can process in a particular moment. Maybe instead of having not 4 thread blocks, maybe we need 40 thread blocks, or maybe we need 400 thread blocks. How are these 400 thread blocks executed? Well, the rest of thread blocks, all these thread blocks that you see here, 4, 5, etc., are just waiting for the first 4 thread blocks, 0 to 3, to finish. As soon as one of these thread blocks finishes, we have one free slot in the SM, and this free slot will be occupied by the next thread block, the next available thread block. It's the thread block scheduler who takes care of that. So this is our entire frontier. Observe that in order to process the entire frontier, we need M thread blocks. So we first launch thread block 0, 1, 2, 3, and when they finish, 4, 5, 6, and so on. So this is what we do in kernel 2, actually. What we could do, if we want to have a more efficient implementation, is using persistent thread blocks. What's the meaning of persistent thread block? The meaning is that we are only going to launch as many thread blocks as can run at one particular moment, can run simultaneously on the available cores. How many thread blocks can run simultaneously? 4, right? So we are only going to launch 4 thread blocks. But these thread blocks are going to take care of all the computation that is needed to process the entire frontier. Something like this. We launch thread block 0 to 3. They start working on these chunks of the frontier 0 to 3. And when they finish, they start working with the rest of the frontier, chunk 4, 5, 6, and so on. Observe that we don't really need to terminate a thread block and launch a new thread block because it's always the same thread block that is running there. The good thing of doing this, of using these persistent thread blocks, is that we can synchronize them without terminating the kernel. We can synchronize them by using atomic operations. Actually, let me show you some code or some pseudocode here. So this would be for the entire kernel 3. We have this while loop while the frontier size is different to 0. That is, while we still have vertices in the output queue, we must keep running. And with this for loop, we distribute the frontier, the vertices in the frontier among all the available threads. We visit the neighbors. We enqueue in the output queue if it's necessary. And when we finish with this for loop, we update the frontier size. That will be checked in the beginning of the while loop, in the beginning of the next iteration, and then we have this global synchronization. How do we synchronize this global synchronization? There might be different possibilities. I'm just going to show you one way of doing this. So in each of the thread blocks, we consider that we have one leader thread, and the leader thread, typically thread 0 in the thread block, okay? So we have one leader thread in each thread block, but we're also going to have a leader thread in the entire GPU. This leader thread of the entire GPU is going to be thread 0 in block 0. So this code here, the global synchronization, is what we do at the end of every iteration of the BFS processing, okay? So when we reach this global synchronization, the leader thread, TID equals 0, TID equals 0, as you see here, TID is thread index. TID equals 0 updates or adds 1 to this atomic variable, and then it won't execute this part because this is only one of the TID equals 0. That one that belongs, you see, because GTID is like the global thread ID. It also considers the thread block ID. So for thread block ID 0 and thread ID 0, it will go through the if. Otherwise, it waits here in this while loop. So this is kind of busy waiting. This thread 0 that belongs to thread blocks that are not thread block 0 updates this counter and waits in this while loop. And in the meantime, the leader of the entire GPU, which has GTID equals 0, waits until all leaders of all the remaining thread blocks have gone through this atomic addition. As soon as they all are there, this grid dim X is the number of thread blocks. So as soon as this counter has the value of the number of thread blocks, we continue. We change the value of this PTR threads run, and then all the threads that were waiting here in this while loop are released, and they can continue execution. This is just one way of doing this global synchronization. By the way, here we are only talking about leaders, thread 0 in each thread block. What happens with the rest of threads of the thread block? They all are waiting in these sync threads. Okay? So this is essentially a brief explanation of what could be our kernel 3 using using this atomic-based block synchronization. So now let's motivate. This is a GPU implementation. We are going to use this GPU implementation on our collaborative implementation. But now let's motivate our collaborative implementation. Essentially, what we are going to do is, by looking at the execution time that is needed for the different frontiers, we realize that depending on the size of the frontier, it might be better to use CPU threads or GPU threads. Let's think about the examples we had before. At the very beginning of the breadth first search, probably the size of the frontier will be very small because we are visiting just a few vertices, and each of the vertices might have many friends in the social network, but we are still considering very few vertices, very few people, very few people, exactly. So in the very beginning, the size of our frontiers is going to be smaller. Once the BFS progresses, the size of the frontier might be much bigger. Here, actually, you see one example that shows the average execution time for frontiers for a particular graph, New York City roads, and you see that the average execution time in this part of the graph and also in this part of the graph is smaller for the CPU than for the GPU, essentially because the size of the frontier at the beginning of the graph processing and at the end of the graph processing is very small. So because we have very low number of vertices in the frontier, it is enough with using CPU threads. We don't need to use all the entire GPU resources. When we have in the middle of the algorithm, the size of the frontiers is much larger, so then the GPU is faster than the CPU. Does it make sense? So that's why we think about this collaborative implementation. Very simple approach, actually, because, or conceptually simple, because depending on the size of the frontier, we are going to use, for small frontiers, we are going to use CPU threads. For large frontiers, we use GPU threads or GPU thread blocks. And we switch from CPU to GPU every time it is needed. So we could have something like this. While our frontier size is different to 0, and depending on this limit, which is the threshold to switch from CPU to GPU switch from CPU to GPU, from GPU to CPU, we will launch CPU threads, or we will launch a GPU kernel. While the size of the frontier is below or above the threshold, we will keep running the CPU threads or the GPU thread blocks using the atomic-based synchronization approach that I explained in the beginning. And here you can just see some results for this collaborative implementation. These results are, again, on the NVIDIA Jetson. Depending on the graph, you might have some improvement or not. For example, here we have some improvement, 15% for this graph. We don't have any improvement for the other graph, but actually it's not bad. Probably, I mean, improvement with respect to the GPU. But actually, this is not bad because the collaborative implementation will always choose the GPU side because it's going to be faster in almost all the iterations. Well, if we don't use unified memory, we need to take care explicitly of the memory copies. If we use unified memory, we don't have to care about that. That's what you can see in this in the slide. And also, if we have new heterogeneous features like the system-wide atomics and like the CPU-GPU memory coherence, it might be even possible to have a data partitioning. In addition to the task partitioning, we could have a data partitioning strategy where we have CPU threads and GPU threads working on the same frontier at the same time. This is something that wasn't possible before that. Here you can see some results. Actually, these results are not for BFS, are for SSSP, single source shortest path. It's a very similar algorithm. A little bit more complex, a little bit more computation, but it's based on the same principles as BFS. And you see for the collaborative approach using GPU plus 2 CPU threads, we obtain up to 22 performance improvement on the AMD Kaveri that we saw previously. And this is the, I almost don't have time to finish, just 7 minutes, but let's very quickly go through this, through the last case study. This is an example of fine-grained task partitioning. In this case, well, this is an algorithm for ego motion compensation and moving object detection. We don't need to worry about the algorithm. We just want to focus on one of the stages of the algorithm is the random sample consensus. This is an algorithm to generate model, and in particular, in this application, we use this RANSAC algorithm to generate a model of the optical flow vectors from a video frame, from the frames of a video stream. So. With the RANSAC algorithm, we obtain the model for the behavior of the optical flow vectors in the background, which are the majority of flow vectors, and actually we can subtract these flow vectors from the background in order to keep only the flow vectors in the moving object, and so that we can find where the moving object is. And this is quite useful when not only you not only have moving objects, but also the background is moving because the camera has a lot of ego motion. Anyway, the thing is that this RANSAC algorithm has different stages, and some of these stages are inherently sequential, while other stages are highly parallelizable. Essentially, the two main stages are the fitting stage and the evaluation stage. In the fitting stage, what we do is generating the model from two randomly picked flow vectors. We generate what is called the first-order flow model. The generation of this model is completely sequential, so it's a good fit for CPU threads, while then we want to evaluate the model, and this is data parallel, because we have to evaluate the model by comparing some kind of virtual flow vectors that have been obtained from the model with the real flow vectors. So, and then we count the number of outliers, how wrong we are in our model. Essentially, we pick two of these models, two of these vectors, generate the model, and then we compare vectors generated using the model with the real vectors, and that's highly parallelizable. So that is a good example of fine-grained data partitioning, because actually this is also an iterative algorithm, and here what we can do, because the vectors are picked randomly, what we can do is having all the iterations at the same time, and each of the threads, like couples of CPU thread and GPU thread blocks, are processing each of these iterations in parallel. As soon as the CPU thread finishes with the generation of the model, with the model fitting, it signals, by using some system-wide atomic operations, it signals the GPU block so that the GPU block starts evaluating the model. And we can get some improvement from doing that. I'm ready to finish. I just want to show you some more slides. You will have the slides, so you can take a closer look later. You can find some code examples for this kind of collaborative approaches in this benchmark suite. There are data partitioning, coarse-grained task partitioning, and fine-grained task partitioning. Here in this slide, you have a list of all the available benchmarks from different fields. And I just want to show you some results on the AMD Kaveri for these codes, the data partitioning, fine-grained, and coarse-grained task partitioning. You see that we are comparing like the discrete version that is using like the traditional collaborative, the traditional way of collaborating with the unified version. This is a version that uses unified memory. In most of the cases, you see that the execution time, the kernel execution time is very similar, especially in these data partitioning benchmarks, because in the end, the amount of computation that you're doing is the same. So if you go back to the Bezier surface, in the end, you have to compute all the points in the surface. There's no way to accelerate the computation itself in the data partitioning. But still, you can get some benefit from the fact that you don't need to care about the explicit data transfers for the in the case of the Bezier surface, for the input control points or for the output surface. And also, in some other cases, you can get some, actually some performance improvement. For example, for BFS, it's very clear, or for this, this is ransack, actually not much improvement, but a little bit. This is another, it's a different thing. This is a task queue system. You also see a lot of benefit from using the fine-grained approach in BFS, because we can switch from CPU to GPU in a much easier way, much more efficient way. We can save a lot of execution time. Okay, so this is the kernel. On top of that, we can add the copy time. You see, copy to device, copy back, and merge, because we have to merge the results from the CPU and the results from the GPU. The improvement for the unified versions using the new integrated heterogeneous features is much higher. And there's only a little problem in this AMD Kaveri, is that the memory allocation, for some reason, takes much longer when we allocate the unified memory. Not always, but in the first touch. For some reason, when we allocate the first byte of this unified memory, it takes much longer than regular memory allocations. This is Interestingly, something that happens in the EMD Cavalry, but doesn't happen in other devices that we have discussed, like the NVIDIA GPUs. And that's all. Just the remaining 2 slides are for FPGA, because also we use these benchmarks on FPGA because they are in OpenCL, and current FPGAs from Intel Altera already support being programmed with OpenCL. It's not as efficient as using VHDL or Verilog, but obviously it's much more productive from the programmer point of view. And this is just some results that show that it is possible to have collaboration between FPGA and CPU as a different example of a heterogeneous integrated system. So that's all. Any questions? Thank you very much. And see you tomorrow.